Hello everyone, this is allLogarithmsEqual, and the next installment in Polynomials' greatest hits is the following. Given a polynomial p of x, and it's really the same thing that I had written last time, so I'll just put this here. Given a polynomial p of x represented as, this same general form, which is a sub n times x to the n plus a sub n minus 1, x to the n minus 1, plus ... for all the possible coefficients of the polynomial, plus a sub 1x plus a sub 0. Then, interestingly enough, the fact for today, and I know this fact that is already written is from the previous episode, so if you'd like to watch that, feel free. But the fact for today is that the mathematical average of all the complex roots of p does not change after differentiation. So to illustrate this, I have another separate slide, which is right here. So if we just take an example polynomial, x to the 7th plus 4x to the 6th minus 3x to the 5th plus 8x to the 3rd minus 7x squared plus 5x plus 3. Then, building upon the previous episode, what we can do is take the average of these roots. And what is the average but the sum of all the roots divided by the number of roots? That's simply how a mathematical average is defined, at least in modern terms. I keep wanting to make a video at some point about different definitions of the mathematical average, and how there are actually several different approaches to it, but that's a topic for a different day. Of course, if we just in modern terms, it just means taking a mean, or a sum of all the roots, and divided by the number of roots. So, in this case, we also know by the fundamental theorem of algebra, by the way, that the number of roots, complex roots that is, to a given arbitrary polynomial, must be equal to the degree of that polynomial. So in this case, we have degree 7. So, at least for p, we're going to want to divide by 7. So we take the sum of the roots and divide by 7. Now, what you'll remember, especially from the previous episode, is that the sum of the roots, we have a formula for that now. We know that that is negative a sub n minus 1 over a sub n. So now, for the case of p, n equals 7. So all we have to do is determine and look to see what a sub 6 is and a sub 7 is. So basically, just looking at these first two coefficients, and what you'll find out is that basically the sum of the roots is negative 4, since we take, negative a sub n minus 1 over a sub n. Again, I guess I chose a monic polynomial, perhaps just by force of habit, but ultimately we just take the negation, because it's monic, we can just take the negation of this coefficient right here, and that's the sum of the roots. So negative 4 is the sum of the roots. If we want the average, we need to divide that by 7. So in this rather simple case, we know that this is negative 4/7. That's the average of all complex roots for p of x. So, what's interesting about this is that we can differentiate it any number of times, and the average of the roots stays the same. That's very interesting. This is new information, relatively new information to me, even, but this is, it's been known for a long time, I bet, but perhaps not very widely known. Okay, so after differentiating, taking the derivative of p of x, we can end up with 7x to the 6th plus 24x to the 5th minus 15x to the 4th plus 24x squared minus 14x plus 5. So that's just taking, directly from p of x right here, differentiating it just by hand, and we can get this. Now, what's interesting is we can take the average of these roots, and again, it's the same procedure every time. We take negative a sub n minus 1 over a sub n, and then divide by n for that given polynomial. So in this case, we take negative 24 over 7, since that's the ratio of these two coefficients. And of course, we have to negate it. So negative 24 over 7 times, and in this case, the degree of the polynomial is 6. So we divide that quotient by 6, and again, after simplification, we can end up with negative 4/7. So it's the same average, the same value that we found the first time. And I'm sure your eyes have already skipped ahead by now to this entire table. So I could go through and describe each of these calculations, but, you know, I don't want to waste that much time, and, you know, you can also verify these by hand or with a calculator to see that they're all true. But indeed, for all the derivatives, if we keep going, if we differentiate that and get p double prime, we can get 42x to the fifth plus 120x to the fourth minus 60x cubed plus 48x minus 14, and that average will still turn out to be negative 4/7 after simplification. And one can prove this rather easily, in fact, and so that's what I'm going to do later on. Perhaps I'll leave an annotation or something to skip to that part of the video, but man, I hope I don't forget that. But anyways, another thing we can do with this fact, with this information, is see the diagrams, the actual complex plane diagrams of all of the n complex roots to these polynomials, each of these polynomials. And so I actually did that using Wolfram Alpha, and I can show you the diagrams that it gave me. So bear in mind our special number, so to speak, for today is negative 4/7, because that is really the number we're looking for each time we take the average of all the roots. So for instance, and I'll set this aside, I suppose. For instance, here is p of x. So again, I entered this into Wolfram Alpha, and you can see what it outputted. I simply requested all the roots to this polynomial. Now, the first thing I did was I actually looked for these, looked for these roots in a program that I wrote, a Java program, but unfortunately I was having trouble pinpointing the actual roots, and I think the reason for that is simply because all of these roots are irrational, or at least all the real roots are irrational. So I was looking for an exact rational root, and I couldn't really calculate it. I could only get some vague estimates, and even then it was unclear, because again, some of them were complex, and I expected that. I expected some complex roots, but I couldn't get it very accurately. Nonetheless, Wolfram Alpha, thank you very much, Wolfram Alpha, it gave me all 7 roots to this beginning polynomial, this p of x, and, perhaps most importantly, you can see this diagram of all 7 roots plotted in the complex plane. Now, first of all, what's also interesting about this, and this is true, interestingly enough, now that I think about it, this is true for all complex polynomials. Any polynomial you can think of with complex coefficients, this must be true. And that is to say that the average of all the roots must be a real number. It must actually be on the real axis. I think there's a complex root theorem for why that's true, but basically the idea is that if we have a root of a polynomial that is not on the real axis, then there must be an equivalent root that is on, so to speak, the other side, the opposite side of the real axis. So it's the same number but with a negation of the imaginary component. It's fine if you didn't catch all that, but that's just an additional point that I wanted to make. Remember, negative 4/7 is the number we're looking for, and the reason is simply because negative 4/7, which should be somewhere around here, is the average of all of these roots. And so I just wanted to show you that, you know, this is the diagram for p of x, but if we were to differentiate it, flip, there's the differentiation, there's actually the first derivative of p of x, so p prime. What you'll find is that, and perhaps this isn't completely perfectly obvious to the naked eye, but it's at least believable, that the center, so to speak, of all of these 6 roots, because, you know, 6, because this is the first derivative, is located somewhere near that that cross that I just made, and that is supposed to be negative 4/7. It's supposed to be that same value. And so, you know, this is a different formation of the roots, but, you know, it's still interesting, because even though all these numbers are different, or at least, yeah, most of them have been altered in some way, the average of all these roots did not change, which is very interesting. If we move on and differentiate this once more, again, we have all new numbers for the roots. You know, negative 3.25, negative 0.73, 2, 0.303, 136, and then 2 complex roots this time, instead of the 4 roots, complex roots, non-real roots that we're used to. Anyways, the point is, all these numbers have changed. You know, the orientation of the roots has changed. However, the average still has not. It's still about, well, I would say about, it's still equal to negative 4/7. And we keep doing this. Let's take the next derivative. Whoosh. There you go, that's the next derivative. And in this case, it's a 4th degree polynomial, so there are 4 complex roots, all different from the last one. And so the axis is slightly, look at this, the interval is actually changed in this diagram that Wolfram gave me. But the idea is that the average is actually still the same, equal to negative 4/7, and you can check that again. Now let's differentiate it again, just to, I don't want to beat the dead horse, but just to show you. So you can see for the 4th derivative of p of x, we end up with a 3rd degree polynomial. So this is looking probably more familiar as, you know, something you'd probably see or study in an introductory calculus class. It's a rather common shape. It's a cubic polynomial with 3 real roots, and in this case, all 3 of them are real. So we don't even have to worry about non-real roots. However, again, you know, and all these values are different. We could prove that this is that these are the roots. We could do that just by factoring out an x and then using a quadratic formula. But I'm not going to waste your time with that. The important thing for this lesson is that the average of the roots has remained the same, negative 4/7, or about negative 0.5714. And taking the derivative one more time, we can see it's a quadratic, which is very predictable, of course. So this is the 5th derivative of p of x. It's a quadratic equation, 2 complex roots, and again, both of them are real. We could again prove this using the quadratic formula, but again, let's not waste time. So the important thing, again, is right about, hang on, negative 0.4, negative 0.6. I'm trying to mark it, you know, mark that cross as accurately as I can. And of course, one last time, just for a finale, we get the 6th derivative of p of x, which is, of course, just a straight line. It's degree 1, so there's only one solution, one complex solution, and that is, as you'd predict, negative 4/7. And it gives us that right there, exactly where it's supposed to be. So thank you all for watching. Oh, I remember what I want to do. I'll prove it for you. Okay. You know, we've just seen it illustrated. But now, on to actually prove this, okay? So, the average of all the complex roots of p does not change after differentiation. That's our theorem, so let's prove it right now. P of x, we know, must be equal to a sub n x to the n plus... Now, I'll just copy over the definition from last time. This is our definition of p of x. We already know to start with that the average of all the roots is equal to, it's by definition equal to the sum of the roots, so sum of r sub I from r equals 1 to n, over the number of roots. And what is the number of roots? Well, that's just n. We already talked about that earlier. By the fundamental theorem of algebra, there must be n complex roots to this polynomial. And so, keep that in mind, because I'm going to store this as a variable. Just remember this formula right here. That's the only important thing. We're taking the sum of all the roots up to n, dividing by n. Now, the next step is simply to differentiate p of x, which in the general case, as you're familiar with, if you've had, you know, any introductory calculus class or any differentiation, you'd know this is equal to n times a to the n times x to the n minus 1, since, of course, we bring down an exponent and then decrement that exponent, plus quantity n minus 1 times a sub n minus 1 times x to the n minus 2, and we keep doing that right until we get 2a sub 2x plus a sub 1. And the average of all the roots in this case... Oh, and I'm sorry, I forgot to simplify this. I meant to do one more step up here, which is to say, what is the sum of all the roots? Well, we know the sum of all the roots for p of x is negative a sub n minus 1 over a sub n. And we're dividing that by n, so we can just leave n in the denominator. So this right here is our main formula. That's very important. Now for p prime of x, we can take negative n minus 1 times a sub n minus 1, which is, of course, this coefficient right here, coefficient of x to the n minus 2, after differentiation. And we're dividing that by this coefficient, the coefficient of x to the n minus 1, and we're dividing that whole thing by n minus 1. Since for p prime of x, there are n minus 1 roots. So there's going to be n minus 1 roots times the coefficient of this right here, which is n times a sub n. And what you'll find, just by looking at this, is that we can actually simplify, we can cancel out the n minus 1 in the numerator and denominator, and we know that this must equal negative a sub n minus 1 over n times a sub n. So we know that the average of the roots has not changed mathematically from p of x to p prime of x, because of course this formula has remained the same. Negative a sub n minus 1 over n times a sub n. So it's still the same value numerically, whether we differentiate or integrate the function. So the average of the roots does not change. There you go. There's your proof. I guess normally if this were an official mathematical proof, I would give more detail, more written explanation, but I'm showing you that verbally. So again, thank you all for watching, and I hope this was rewarding too. I hope it was interesting. Yeah, that's about it. Please stay tuned for the next installment in Polynomials Greatest Hits, the next track, I guess. Yeah, see you all next time.